In its first few 100 million years, the cosmos looked very different. Gas and dark matter clouds were just starting to coalesce as gravity took hold. It was also around this time that the first stars composed entirely of hydrogen and helium began to develop astonishingly, however. By this time, some enormous black holes with masses of up to 1 billion stellar masses had developed in the standard model of black hole creation and growth. It would take billions of years for a black hole to expand to 1 billion solar masses, and the universe is less than 1 billion years old. Furthermore, if the present models of black holes are correct, then quasars and other extremely massive black holes should not have developed during that time period, but they were actually around in the primordial cosmos when the cosmos was young. How did the largest black holes form? How did they put on so much weight in such a short amount of time, only a few million years after all is said and done? How does this new information affect our present knowledge of black hole birth? First, let me give you a quick overview of what a quasari is. It is a supermassive black hole that spins very quickly and consumes plasma at the core of a faraway galaxy, a phenomenon known as an active galactic nucleus. Quasars are extremely luminous and strong things in the cosmos. The brightness of some quasars can be billions of times that of our own Milky Way. The fascinating mystery, though, is what gives these things their incredible strength. Of course, quasars are typically found in galaxies with extremely high gas abundances. As the gas falls into the black hole in such a dense area, it heats up as it swirls around the event horizon. That's why it gives off radioactivity across the board in terms of frequency. Generally speaking, quasars are only discovered in extremely remote galaxies because local supermassive black holes do not have such large amounts of gas. Markarian 231 is one of the closest quasars, but it's still about 600 million light-years away. The question then becomes, how do such majestic, revolving constructions come into being? There are currently two major hypotheses that can account for the overall creation of black holes. According to the first and most popular hypothesis, the death of a large star can result in the creation of a black hole, with a mass of up to about 100 times that of the Sun. With enough time, this dark vortex can swallow its surroundings, causing the black hole to expand in size until it attains a supermassive state with a mass of several million to several billion times that of the Sun. But experts agree that no black hole could ever devour enough matter in 500 million years to reach the mass of a billion suns. This is because as material falls into a black hole, it forms a circle called an accretion disk. As it orbits the black hole, the material in this ring achieves velocities close to those of light. As a result of the g-forces, the disk heats up and emits a wide range of rays. This radiation exerts such a strong force that it drives away adjacent matter, slowing the black hole's rate of mass ingestion. The theoretical upper bound on a black hole's growth rate is determined by the Eddington mass. Even if a black hole is capable of sucking in matter at a rate greater than the limit, the increased accumulation is still likely to result in strong gusts. The development will be halted as the nearby material is blown away by the strong gusts. The rate of black hole growth is capped by these variables. If this situation plays out, it would run counter to the idea that quasars formed in the normal manner in the early universe. Now we can discuss the alternative hypothesis for how quasars originate according to it black holes with masses up to 100,000 times that of the Sun formed when short-lived stars, some of which may have had lives of nearly 250,000 years, eventually imploded. Since this black hole was so enormous, it could have easily accreted billions of stellar masses in a short period of time. Furthermore, it is estimated that the initial mass of a quasar must be between 10,000 and 100,000 stellar masses, which lends credence to this hypothesis. However, the parent star must be exceedingly massive, nearly tens of thousands of times more massive than the Sun, for such a black hole to develop. However, such enormous stars have never been seen before in the observable cosmos. Even the heaviest star ever found is only about 300 times as big as the Sun. Additionally, there is no known process that can currently propel the creation of stars with masses many times that of the Sun. But we also know that circumstances in the early cosmos were different from what we see now. As a result, such stars could have developed in the early cosmos, as shown by simulations. Massive stars might have developed at the intersections of strong streams of dense and turbulent cold gas, but this would have been an extremely uncommon occurrence. However, in order for stars to develop, extremely bizarre circumstances would have had to exist, such as strong ultraviolet radiation or supersonic movements between gas and dark matter. To make matters worse, none of these out-of-the-way places have circumstances that are even remotely like those in which the first quasars were discovered. In that case, how do we account for the emergence of quasars? Scientists simulated the flow of the gas to get an idea of the solution to this query. A newborn star is typically formed when a compact mass within a cool cloud falls due to the cloud's own gravity. However, such a fall cannot occur in the presence of substantial disturbance. Because of this, the models showed that the creation of typical stars, like the ones we see today, was inhibited by the turbulence produced by the stream's intersection. This instead caused the cloud in the simulation to expand so large that it disintegrated violently into two enormous stars, nearly 31,000 and 40,000 times. The mass of the Sun, a supermassive black hole, billions of times. The mass of the Sun can develop and expand in just a few 100 million years, if the gas from the streams continues to fuel the clouds. This explains how, even in the absence of unusual circumstances, supermassive black holes could have developed at the crossroads of gas streams. And if the numbers hold, about 200 quasars were born in the first billion years of the universe's existence, it's possible that we figured it out. Now, one of the study's authors, Daniel Whalen, put it this way: the first supermassive black holes were merely a natural result of structure formation in cold dark matter cosmologies, offspring of the cosmic web. This is a stunning concept too. In order to ensure that you don't miss future episodes of this series, please like this video, subscribe to our channel, and click the bell symbol. Thanks for watching. I hope you enjoy it. A supernova is the largest eruption ever observed by humans. Each detonation is the incredibly brilliant and incredibly powerful outburst of a star. One variety of supernova is caused by a dying massive star's last effort. This occurs when a star with at least 5 times the mass of the Sun explodes with a tremendous explosion. Massive stars consume vast quantities of nuclear fuel in their centers or cores. This generates enormous amounts of energy, causing the center to become extremely heated. Pressure is produced by heat, and the pressure produced by a star's nuclear combustion prevents the star from collapsing. A star maintains equilibrium between two opposing forces. Gravity attempts to compress the star into the smallest, most compact spheroid possible. However, the burning of nuclear fuel in the star's interior creates a significant outward pressure. This outward thrust resists gravity's inward compression. A huge star cools down when it runs out of propellant. This results in a decrease in pressure. Gravity triumphs, and the star collapses abruptly. Imagine something with a mass 1 million times that of the Earth, disintegrating in 15 seconds. The collapse occurs so rapidly that it generates a mint shockwave that causes the star's outer region to erupt. Typically, a dense nucleus and an expanding cloud of hot gas termed a nebula are left behind. A supernova of a star greater than approximately 10 times the size of our Sun may leave behind black holes, the densest objects in the universe. Think about being an astronomer at the start of the 17th century. As the telescope has not yet been developed, you must use your limited vision to explore the universe. Then one day, you see a truly spectacular scene. In the next several weeks, a new star will shine brighter than Venus. Very high levels of brightness make it visible throughout the daytime. As the months pass, it fades somewhat, but persistently in the sky. The Middle East and Asia all witnessed the same thing that the German astronomer Johannes Kepler did in 1604. Now we know it was a supernova explosion, a massive explosion that occurs when certain stars approach the end of their lifetimes, and not a new star. The latest supernova to occur within the Milky Way was in 1604. Maybe more nearby supernovas have occurred since then, but they have been veiled by interstellar gas and dust, and hints have not been noticed. The Crab Nebula is an example of a remnant of a supernova that occurred thousands of years ago. Its light reached Earth around 1054. The supernova discovered in the Large Magellanic Cloud in 1987 was the closest thing to Kepler supernova in recent years. In addition, several supernova and other galaxies have been documented. These may be seen with the naked eye, but only with a telescope. Sky watchers in Kepler's day would have missed them totally. Hence, it has been 418 years since we last witnessed a star explosion in our galaxy is a close brilliant supernova. Therefore, long overdue scientists predict that between 1 and 3 stars should burst in our galaxy per century. If the next supernova occurs, modern astronomers will be better prepared for it than Kepler was or even scientists from only a few decades ago. Astronomers now have access to telescopes that can record visible light. When used together, these equipment will simulate the experience of flying near to a supernova and observing it with our own eyes. In addition, we have telescopes that are sensitive to infrared light, or light with wavelengths that are beyond the red end of the visible spectrum. Infrared light, with its longer wavelengths, may penetrate gas and dust more easily than visible light, allowing us to see objects that might otherwise be hidden from view with conventional telescopes. Examples of instruments that predominantly record infrared include the James Webb Space Telescope. The electromagnetic spectrum includes both visible and infrared light. However, neutrinos, which are subatomic particles, are also emitted by supernovas, and modern detectors can capture them. Also, astronomers now have detectors that can record gravitational waves, which are tiny vibrations in the fabric of space-time, thought to be released by exploding stars in the scientific literature. 2 kinds of supernova have been identified when a white dwarf star undergoes a Type 1 supernova. It sucks material off of a partner star until a runaway nuclear reaction occurs, causing the white dwarf to be blown apart and send debris hurtling into space. As the star runs out of nuclear fuel, it collapses under its own gravity and bounces, setting off an explosion known as a Type 2 supernova. There have been instances of both types of supernovas being brighter than their host galaxy, combined with the tremendous amount of neutrinos that are released, alongside the light, making Type 2 supernovas. Very fascinating neutrino emissions can actually begin before the explosion happens. Even though the field of neutrino research was in its infancy when the explosion of 1987 occurred, 3 detectors were able to record a total of 24 neutrinos. One may expect hundreds, if not thousands, of neutrinos to be recorded by the global network of detectors should a supernova burst within our galaxy at this time. At this time, very provocative signals might be produced in the event that a falling star forms a black hole, therefore preventing the explosion from producing any further stellar debris. In those conditions, the neutrino stream would abruptly cease. It would be awesome if you could see the black hole's sharp boundary, which indicates its formation. The missing star might then be identified by comparing it to other stars in astronomical databases. A lost star might be the site of a freshly generated black hole. Successful discovery of gravitational waves from a galactic explosion would round off the hat trick. Gravitational waves, which Einstein said would exist when a huge body was accelerated, are distortions in space-time that are produced as the mass of the body accelerates. Such signals were identified for the first time in 2015. Black hole and neutron star mergers are responsible for the gravitational waves seen so far, yet when a supernova does occur in our galaxy, it should also be seen. Computer models of supernova explosions have been used by astronomers for decades, but many features remain unknown. Knowledge gained from studying gravitational wave data may shed light on the method and what danger a close supernova may pose to life on Earth in principle. Yes, but the explosion would have to be quite close, since there are currently no nearby stars in danger of exploding. To be sure, a close supernova's radiation outburst would be disastrous, so this is excellent news. The explosion would release harmful UVX and gamma radiation into space over a period of weeks, damaging Earth's protecting ozone layer. Even if they didn't reach the ground, without the ozone layer, the sun's lethal UV radiation would flood the planet, killing everything from phytoplankton in the oceans to humans. It's possible that something like this occurred sometime in Earth's past around 360 million years ago. Near the close of the Devonian epoch, a massive extinction may have been caused by a supernova. On the other hand, supernova are not just destructive forces, they may also give rise to new life. Astronomers and physicists point out that the nuclear processes that take place deep within exploding stars and spread throughout space, as a result of the blast waves they create, are the source of many of the heavy elements on which humans depend. This means that a supernova would be the new gold standard for astronomers. Thanks for watching, hope you enjoy it. Every tale commences somewhere, and this holds true even for the narrative of the cosmos. Approximately 13.7 million years ago, an enigmatic occurrence propelled the universe into motion, marking the advent of the Big Bang, an extraordinary event that gave rise to every atom, star, and galaxy. However, what unfolds here is uniquely ours, a saga spanning millennia, where we've endeavored to construct a vision of the universe. This endeavor, guided by the principles of science, has allowed us to fathom our place within the vast cosmos. Over thousands of years, we've documented our celestial observations in volumes that could easily populate a library. The edifice of knowledge we've erected regarding our universe encompasses its origins and contemplates its eventual conclusion. So where does our narrative commence? Let's embark on this journey from the very outset. Let's delve into Genesis, starting with the monumental event known as the Big Bang. The concept of the Big Bang serves as a framework for understanding the cosmic evolution and unfolding narrative that illuminates how the universe transformed in the blink of an eye, and the very nature of what sparked this cosmic genesis remains an unsolved puzzle to this day. As we appear into the vastness of the universe and contemplate distant galaxies, a mesmerizing panorama unfolds. Everything appears to be receding from us, propelled outward at astonishing speeds. We string that all the way back, we glimpse a singular moment, perhaps 13 or 14 billion years in the past. where all matter was inexplicably condensed into an inconceivably dense point. The Big Bang stands as our prevailing theory, a testament to our attempts to decipher the universe's inception for an extended period. Contemplation of the universe's origin was not a common pursuit. Some didn't dwell on it, while others assumed the cosmos had perpetually existed, an everlasting entity, shrouded in mystery. Initially, even scientists hesitated to embrace the concept of the Big Bang, originally intended as a somewhat derisive term. The name itself poses a paradox. It wasn't particularly big, considering our belief that the universe originated from a singularity, and there was no literal bang, since there was no air to transmit vibrations today. The Big Bang theory is a well-established pillar of science, widely accepted and understood. However, acceptance and comprehension are distinct realms. While the Big Bang theory has solidified its place in our understanding of the universe, it hasn't yet unraveled all the mystery science seeks to answer about the birth of our cosmos. Conventional Big Bang theory remains silent on what triggered the bang, why it occurred, or what transpired before it. At this very moment, we find ourselves in the aftermath of the Big Bang. Everything we see, hear, taste, smell, and touch is an aftermath. This is the Earth, a marvel of silicon and oxygen encasing a metallic core. Its surface is dominated by vast oceans, fostering a diverse array of life in a rhythmic dance. The Earth completes a full rotation every 24 hours, while encircling the radiant star known as the Sun, completing an orbit every 365 days. The Sun is a radiant giant predominantly composed of hydrogen and helium, with a scorching surface temperature nearing 10,000 degrees Fahrenheit. This cosmic powerhouse converts a staggering 700 million tons of hydrogen into 695 million tons of helium every second. This celestial luminary is at the heart of our solar system, which took shape approximately 4.5 billion years ago. This system has 8 planets, from the sweltering Mercury to the frigid Neptune. Our solar system is no static entity hurtling through space at a staggering 134 miles per second. It is part of a vast congregation of stars and stellar systems. This constellation, known as the Milky Way galaxy, has around 200 billion stars. Among these, an estimated 6 billion may harbor planetary systems akin to ours. Our solar system, orbiting the center of the Milky Way on one of its outer arms, is just one member of a grand ensemble. The Milky Way is merely one among the vast expanse of more than 125 billion galaxies constituting the observable universe. Indeed, the universe is colossal, and its enormity continues to expand. If we rewind time, we can witness the universe contracting, shrinking from a cosmic scale to a galactic one, then to the dimensions of our solar system, and further still until everything is confined within the confines of a studio, a coffee cup, and ultimately an atom. The vastness of the universe unfolds before us as a cosmic narrative expanding across unimaginable scales. Physicists have pieced together an approximate timeline of significant events in the cosmos' existence using telescope data and models of particle physics from its beginning to its inevitable demise. We examine key points in the evolution of our universe in the cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. But further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius. Just a few milliseconds after the Big Bang, quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances in both terrestrial atom smashers and the early cosmos. The challenging to achieve condition only lasted for a few fractions of a second. The early epoch and subsequent period of time, perhaps in the neighborhood of a few thousands of seconds following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons, and neutrons fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet this procedure ceased as the temperature dropped. As temperature settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms, the cosmic microwave background. A remnant of this epoch, first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. During the Dark Ages, there was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic Dark Ages refer to this time frame of around 100 million years because practically all of what astronomers know about the cosmos can be gleaned by studying starlight. This era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies. The cosmos entered a period known as the cosmic dawn or reionization. It's hard to put a time limit on reionization as it happened so soon after the Big Bang that its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars visible from 12 billion light-years away switched on and began emitting their bright beams of light. Throughout the universe's middle years and the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago. In one galaxy, these accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the Sun retained a lot of water via this process, or it received a deluge of ice and water from comets. Later on Earth, and humanity, little primitive bacteria, appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged capable of contemplating the vastness of space and learning about the universe's origins. The end or not, it isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy. The unknown factor thought to be accelerating the expansion of the universe is that all the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternately, the Great Crunch, a reversal of the Big Bang, in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility. If dark energy accelerates everything apart to greater and greater distances, the universe is a vast and mysterious place, filled with countless wonders and secrets waiting to be discovered among the many mysteries of the cosmos. One of the most fascinating and profound is the age of the universe itself. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Scientists have spent decades studying the universe, using a variety of tools and techniques to unravel the mysteries of our cosmic past. Through their efforts, they have determined that the universe is estimated to be around 13.8 billion years old. The search for the age of the universe began in the early 20th century, when astronomers first realized that our universe was expanding. The concept of an expanding universe was first proposed by Belgian astronomer Georges Lemaitre in 1927. But it wasn't until the work of American astronomer Edwin Hubble in the 1920s and 1930s that the idea was widely accepted. Hubble's groundbreaking observations of distant galaxies revealed that they were moving away from us at great speeds, and that the farther away the galaxy was, the faster it was moving. This relationship, known as Hubble's law, suggested that the universe was not static, but was instead expanding. If the universe was expanding, then it must have been smaller in the past, and this realization led scientists to wonder just how old the universe was. The first attempts to estimate the age of the universe were based on models of stellar evolution. Scientists knew that stars undergo a predictable sequence of changes as they age, and they thought that by studying the properties of stars in our own galaxy, they could determine the age of the universe. However, these early estimates were plagued by uncertainties in our understanding of stellar revolution, and they varied widely from a few million years to several billion years. It wasn't until the 1960s that a more accurate method for determining the age of the universe was discovered in 1964 too. Astronomers named Arno Penzias and Robert Wilson discovered a faint background radiation that was present in all directions of the sky. This radiation, known as the cosmic microwave background, CMB, is thought to be the leftover radiation from the Big Bang. The event that marked the birth of the universe, the discovery of the CMB, was a major breakthrough in our understanding of the universe, and it provided scientists with a powerful tool for estimating the age of the universe. By studying the properties of the CMB, scientists could infer important details about the early universe, such as its temperature and composition. This information in turn could be used to estimate the age of the universe. Over the next few decades, scientists will refine their measurements of the CMB and improve their understanding of the early universe. They will also develop more sophisticated models of cosmic evolution that take into account the effects of dark matter and dark energy two mysterious substances that make up the majority of the universe. Scientists arrived at an estimate for the age of the universe of 13.8 billion years. This estimate has been confirmed by a variety of independent measurements, including observations of distant supernovae and the large-scale structure of the universe. The age of the universe is one of the most well-established facts in cosmology, and it has profound implications for our understanding of the cosmos. The age of the universe tells us that our universe has a long and fascinating history, stretching back billions of years to a time when the universe was just a tiny, hot and dense singularity. It tells us that the stars and galaxies we see today are the result of billions of years of cosmic evolution, driven by the forces of gravity and the interplay between matter and energy. 13.8 billion years old, why is it still expanding at an accelerating rate? What is the nature of dark matter and dark energy, and how do they shape the evolution of the universe? How did the first stars and galaxies form? And what was the nature of the universe in its earliest moments? These are just a few of the many questions that cosmologists are working to answer. The age of the universe provides a crucial piece of information in the quest to understand the cosmos, but it is just one piece of a much larger puzzle. One of the most fascinating aspects of the age of the universe is how it connects to the fundamental nature of space and time. According to Einstein's theory of general relativity, space and time are intertwined, forming a four-dimensional fabric known as space-time. This fabric can be warped and distorted by the presence of matter and energy, leading to phenomena like gravitational waves and black holes. The age of the universe tells us that space-time has been evolving for billions of years, stretching and warping in response to the forces of the cosmos. It tells us that the very fabric of the universe has a history, and that the structures we see today are the result of an intricate interplay between space-time, matter, and energy. While the universe is expanding at an accelerating rate today, it is still unclear what the ultimate fate of the universe will be. Some theories suggest that the universe will continue to expand forever, eventually becoming a cold and dark place devoid of stars and galaxies. Other theories suggest that the universe will eventually collapse in on itself, leading to another Big Bang and the birth of a new universe. Whatever the ultimate fate of the universe may be, the age of the universe tells us that we are living in a remarkable moment in cosmic history. We have the opportunity to study the universe at a time when it is still evolving and changing, when stars are still being born, and galaxies are still colliding and merging. By studying the universe and its evolution, we can gain insights into the fundamental nature of the cosmos and our place within it. The age of the universe also provides us with insights into the likelihood of intelligent civilizations existing elsewhere in the cosmos. If life is a relatively common occurrence in the universe, and if the conditions for the development of intelligent life are present on other planets, then there may be many civilizations out there that are much older and more advanced than our own. Moreover, the age of the universe has implications for our search for extraterrestrial life. By studying the conditions that lead to the emergence of life on Earth, and by exploring the diversity of life forms on our planet, we can gain insights into the types of environments and conditions that might be conducive to the emergence of life elsewhere in the universe. Some theories suggest that the universe is just one of many in a multiverse, a vast and complex network of parallel universes with their own unique properties and histories. The age of the universe tells us that if a multiverse does exist, then there has been ample time for the emergence of many different universes, each with its own unique history and destiny. Finally, the age of the universe reminds us of the incredible beauty and wonder of the cosmos. From the cosmic microwave background radiation left over from the Big Bang to the intricate dance of stars and galaxies across the night sky. The universe is a rich and complex tapestry of phenomena that is both inspiring and humbling in conclusion. The age of the universe is a remarkable fact that has profound implications for our understanding of the cosmos and our place within it. It tells us about the origins and evolution of the universe, the potential for extraterrestrial life, the nature of reality itself, and the beauty and wonder of the cosmos. As we continue to explore the mysteries of the universe, the age of the universe will remain a key piece of information guiding us in our quest to understand the cosmos and our place within it. The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us, from the mysteries of quantum mechanics to the mind-bending properties of black holes. The universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. This video lets you see some of the many things we do not understand in the universe and the strange and surreal paradoxes in what we think we understand. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Everything we know represents just 5% of the universe. What is the rest? Normal matter, protons. Neutrons and electrons make up just 5% of the universe. Staggeringly, the other 95% is something that we cannot fathom seeing or understanding. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light, but scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, height, and 1 dimension of time, making a total of 4 dimensions in space-time. This is known as the 4-dimensional space-time. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions, but these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional space-time can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature, including the strong nuclear force, the weak nuclear force, The electromagnetic force and gravity, do these higher dimensions exist? And if they do, is there a way for us to measure their presence, or will we forever be trapped in our four-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse, theory is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we can't travel backwards in time. Why are we trapped in the arrow of time, perpetually moving forward? Is the passing of time intertwined with the way our universe works, according to the theory of the Big Bang? Time itself began together with the rest of the universe, about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past through the present and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis in the context of physics. Time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the four-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness in a closed system, tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature in certain situations, 2 particles can seemingly be an instant connection with each other. Even if they are located at opposite ends of the universe, the phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So, while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances. Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare, or does it have a limited lifetime, destroying itself before it has the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask, given the vast size and age of the universe. It seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places. Yet our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit. So when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us. But why is this? Why do the fundamental circumstances of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together, exactly as it was before the principle of entropy moved the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale. Likely trillions of years in the future, can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it is past the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole. Where the laws of physics as we know them break down, we do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions. There it is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in space-time. However, there is no direct evidence to suggest that wormholes exist, and the universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning as we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time. We can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us onto new and unexpected ways, spurring us onto new heights of discovery and understanding. We used to only know about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very violent. Planets are made the same way. Everywhere they come from the dust and other things that are left over after stars are born. So if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our solar system, but now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400, some of which are huge spinning balls of gas that are 5 times as big as Jupiter. Others are huge rocky worlds many times larger than Earth. And some follow wild erratic orbits so close to a star they're burning up. One thing is clear, no 2 planets are the same, each one is unique, but most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8th circle of our Sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So at the beginning of the solar system, there was a pretty even mix of silicate water, vapor, hydrogen, a lot of hydrogen, methane, and other thing. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you'd mix the ingredients just like you did with the cake. Then you'd put it in the oven and bake it, and it would change. So basically this is what happened in the solar system. Overall, the planet cooks in a slightly different way, depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in it, might not have any rocky planet, because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants, and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids. And these very small mineral grains can start to form these tiny pieces of rock. And minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, and they would basically hit each other and make one slightly bigger dust molecule, and they'd keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid for Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere to become round. A growing planet needs to be 500 miles across. Then it has enough gravity to crush it into a sphere any smaller, and it stays in a regular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now they have to make it through a time of violence and destruction. A cruel time that will decide which planets will live and which will die after the sun was made. All 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition. Derby planet hit planet, most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planet testimony started to grow at the expense of the others, and these things that would eventually become planets grew and grew as they got bigger. They sucked up all the smaller planet testimons around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left because of the things that happened to each planet in the past. They are all so different from each other. Mars is a frozen waste land. Earth flows with liquid water. Venus is a place full of volcanoes, and Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense, so it could have been a bigger planet in the past. Then something hit it at an angle which tore off the lighter crust and left only the dense center also hit. Hard was the young Earth at the end of the Earth development. It was hit by something else which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history which blew off a lot of its crust, and that crust started to build up again in the south of Mars. There were 2 effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal-rich, those chunks would tend to descend down into what was becoming the core, where if you collided with something light or icy, they would tend to just float about and form part of the crust. Instead, near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron, surrounded by a layer of liquid iron, and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials, but each of them was very different. Different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the Sun. Strong magnetic fields are made by the Sun. These fields rise up in giant loops above the surface, and when they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash, and that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye. And you see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the Sun between 2 moon missions that would have killed the astronauts if they were there. So radiation in space is a big deal, but here on Earth the solar wind doesn't pose much of a threat, because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy deep inside the Earth. The same thing happens as the Earth spins. The hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, But today, it's cold and dry and there's not much going on. So why have the two planets changed so much? NASA sent two robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert, with only one atmosphere of Earth. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away in a few places. We can also see ripples that are made when water flows over sand. So not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point, and because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go early in the planet's history? Mars apparently had a strong magnetic field, and it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly, which means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop, the flow stops, and the magnetic field disappears. As soon as the magnetic shield stops working, the solar wind blows away the atmosphere, and the water evaporates. Mars turns into a cold, empty place. Mars, Earth, Venus, and Mercury all formed within 150 million miles of the Sun, but 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, and Neptune all have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here. 500 million miles from the Sun, at the start of the solar system, there was some dust, but mostly gas and water frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big, because there was so much ice and gas. Their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger. They got more and more dust, and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all 4 of the gas giants, but Saturn's are the most obvious from far away. Saturn's rings look like a single flat disk, but in reality they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time, some of them turning into small moons, some of them falling apart, but they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet Saturn's gravity, which tore it to pieces. All of that stuff got stuck in rings that went around the planet, but the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them, but nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface, but we don't know what's happening inside far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. On December 7th, 1995, Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up as it fell. It measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth when you're in the environment of a gas giant and you go deeper and deeper into this soup of hydrogen, which has no solid surface. It can still be very heavy. And so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery, like some rocky planets. The gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation, and this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields. Because they're so big, these auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets on Earth? The job is done by a very hot liquid metal that spins around the planet's solid iron core. Most likely gas planets do about the same thing. But gas planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice. So we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior. So it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing one planet in our solar system. lost its atmosphere, and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are after all the blue planet, that means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the metal. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away. When things hit these massive collisions that formed the Earth, were so energetic that if there had been water here, it would have evaporated and then left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons, at least half of the water on the moons of Jupiter. Saturn, Uranus, and Neptune, a lot of water was out there. So how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the Sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the massive water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us Homo sapiens to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be, and it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there, and that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So water is everywhere in the universe, and we're finding that planets are too, but we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists, and our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. So it remains an extraordinary holy grail for humanity to find other abodes that remind us of home, but we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration. In the future, we'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place, with the right amount of water. One thing is certain, there are billions of planets out there waiting to be discovered. Our Sun, positioned at the center of the solar system, serves as the primary source of light, heat, and crucially life. However, the trajectory of its future is a subject of inquiry for scientists who are peering into the vastness of space. For answers, these scientists, akin to contemporary prophets, foretell a potentially apocalyptic fate for our Sun. The implications are astounding. The Earth's surface, temperatures projected to reach levels capable of melting rock, and indeed the entire planetary surface. Scientists are aware that at some point in the future, the Sun will undergo fundamental changes that will impact the planets in our solar system. Picture fast-forwarding 7 billion years ahead to witness the solar system's eventual demise. This foresight is possible because the transformations anticipated for our Sun are already observable in numerous other stars. Among these stars, some are referred to as solar twins due to their striking similarities to our Sun. The study of solar twins is crucial not only for comprehending the Sun itself, but also for gaining insights into the future of our solar system. In 2013, scientists identified a solar twin named Karate Sol 1, situated in the Monaceros constellation. Karate bears a resemblance to the Sun in terms of both mass and other characteristics. However, astronomers made a noteworthy discovery. Karat Sol 1 exhibited a lower concentration of lithium, a key element that facilitated an accurate determination of its age. It turned out that this star is slightly older than the Sun by a few billion years. By observing stars older than our Sun, scientists can glean valuable information about the Sun's future trajectory. As the Sun ages, it will undergo a significant increase in brightness. This heightened luminosity is a result of an ongoing internal transformation within the Sun, where two opposing forces engage in a constant struggle. These forces are akin to those influencing a hot air balloon, with the immense pressure of hot gas pushing up and outwards within the Sun. This pressure is generated by the process of nuclear fusion, where hydrogen is converted into helium. The Sun has sustained this fusion process for billions of years, marking its enduring battle against gravity. The Sun's life is essentially a perpetual conflict between gravitational forces attempting to compress the star and the outward. The thermal pressure exerted by the gas, the delicate equilibrium between these forces, has kept the Sun stable for 4.5 billion years, however. With the passage of time, this balance is gradually shifting as the Sun continues to fuse hydrogen. It produces an astonishing 600 million tons of helium every second. The alteration in density has a profound impact on nuclear reactions. As the core becomes denser, the rate of hydrogen burning increases, akin to turning up the burners. This translates to an escalation in the energy emanating from the core. Consequently, our Sun is becoming 10% brighter with each passing billion years as it ages. The solar system experiences a rise in temperature. Scientists are aware that this ongoing process will eventually lead to significant consequences. The habitable zone where the Earth resides orbits a band around the Sun and is characterized as the habitable zone because it maintains the ideal temperature for liquid water. This unique condition makes Earth the sole planet in the solar system where life can thrive. However, as the Sun intensifies its power, the habitable zone will undergo a shift to glimpse Earth's potential fate. 2 billion years from now, astronomer Professor Lynn Rothschild suggests looking to Venus. Venus is visible in the sky, positioned as the brightest object following the Sun and the Moon. Venus and Earth share a common origin, composed of similar materials and roughly the same size. The key distinction lies in Venus's proximity to the Sun, resulting in its higher temperature compared to the Earth. Interestingly, despite being farther from the Sun, Venus is even hotter than Mercury. In 2006, the Venus Express probe was launched to study Venus's atmosphere in unprecedented detail. Analysis revealed a crucial clue among the clouds regarding Venus's elevated temperature. The Venus Express provided insights by detecting a significant amount of deuterium, a heavy form of hydrogen indicating the presence of water in the planet's past. It became evident that Venus was once a drastically different world, resembling a beautiful water world. Not unlike Earth today, there existed liquid, water, reasonable atmospheric pressure, and organic compounds on Venus. In the past, the available evidence strongly suggests that Venus was once situated in the habitable zone, making it a plausible environment for life. Approximately 3 billion years ago, as the Sun's luminosity increased, it had a terrible impact on Venus's water. The rising temperature of the Sun had a cascading effect on Venus. As the Sun's heat intensified, the surface of Venus heated up, causing the water to transform into steam. Since steam is a greenhouse gas, it possesses the capability to trap solar radiation. Consequently, akin to a greenhouse, the temperature on Venus started escalating continuously. It appears that a runaway greenhouse effect played a pivotal role in making Venus the hottest planet in our solar system. While Mercury is closer to the Sun, it lacks both an atmosphere and water. In contrast, Earth possesses both of these essential elements as the Sun becomes brighter and evaporates our oceans. The impact on the Earth is expected to be significantly more severe than the currently observed effects of human-induced global warming over the course of the next 2 billion years. Earth's temperatures are set to soar, presenting a stark challenge for life to either adapt or face extinction. Approximately 500 million years from now, some regions could experience temperature increases of up to 20 degrees. This climatic shift will drive a profound evolution in life as we currently understand it, similar to the way present-day animals adapt to survive harsh conditions. Future generations may employ comparable strategies to endure scorching summers. Consider a bear as accustomed to hibernating in winter. A future scenario could reverse this pattern, with animals opting to hibernate during the scorching summers and remaining active in the cooler winters. Grasses may adapt by setting seeds in spring, ensuring the survival of the plant through the harsh summer, germinating when autumn rains return, and flourishing in the winter in less than 1 billion years. The greenhouse effect is anticipated to intensify, causing temperatures to escalate dramatically as the land becomes hotter. Even winters may become inhospitable for most organisms. Warm-blooded large animals like bison, unable to adequately cool down in the increasing heat, may face extinction in just over 1 billion years. The once thriving land could transform into a barren desert devoid of life. The atmosphere will heat up more rapidly than the water, leading me to predict that, similar to the ancestors of dolphins, the descendants of bison may need to transition from land to water for survival. Projections indicate that in 2 billion years, even the water will have disappeared as it evaporates, and the Earth will increasingly resemble the present day, Venus, in less than 3 billion years. The prevailing belief is that the scorching sun, combined with a runaway greenhouse effect, will likely eradicate nearly all life on Earth. But intelligent life may just find a way out. What sets us apart from other organisms is our possession of technology. This advantage may provide us with the option to migrate to other planets as the Earth becomes inhospitable as it heats up beyond tolerance. Mars could become a more viable habitat. The potential for life on Mars is uncertain, but with our technological capabilities, it's a possibility. Who knows? I have great faith in our descendants. On a night in early September 1859, people all over America could see the aurora. It was blood red and so bright that when miners in the Rockies came out of their tunnels, they thought the sun was coming up so bright. In fact, that even at midnight, you could read a newspaper. It didn't just happen in the US. People all over the world saw these auroras. No one knew why they had happened. But earlier that same day, an astronomer had seen something on the sun's surface that he called a white light flare. Back then, the flare and the aurora seemed to have nothing to do with each other. But we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. And if this violent event happens again, it could destroy our modern technological world. The sun is the most familiar thing in the sky. It gives all life on Earth, heat and light. It is so big that it's hard to imagine, and it makes up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and was made by the burning of hydrogen and helium for the last 5 billion years. But from an astronomical point of view, it's nothing special. A G main sequence star, also known as a yellow dwarf. But looks don't always tell the whole story. Solar flares and explosions of plasma particles and radiation creation from its surface travel far into space. We call this process the solar wind. Solar storms, on the other hand, are very violent eruptions, and a corona mass ejection, or CME, is the most dangerous because it has the potential to bring our high-tech society to its knees. Today we'll find out how bad ACME could be and what astronomers are doing to keep an eye on our star to try to predict when they might happen. Step back in time to 1859. First, in Victorian Britain, it was okay for a gentleman to be interested in solar astronomy, and one man did it in a very good way. Carrington Richard Christopher, we don't know what he looked like though, because there are no known portraits of him. Carrington learned many important things from what he saw. He saw the different latitudes rotated at slightly different speeds, which meant the sun wasn't a solid body, but a fluid one. But he also saw that sunspots could be the start of a solar storm. On Thursday, September 1st, 1859, there were no clouds in the sky in the morning, so Carrington was doing what he always did, which was to look for sunspots. He was using his telescope to project an image onto a screen. At 11:18, he saw two brilliant beads of blinding white light appear in what Carrington calls a kind of configuration. Strangers? Still, they were gone after 5 minutes for no clear reason. Carrington had seen a coronal mass ejection, which was a huge magnetic explosion, a huge cloud of charged particles that are thrown off the sun's surface. After 18 hours, the Earth was hit by an electromagnetic storm. People started calling it the Carrington event. At the time, everyone was talking about the beautiful aurora, which could be seen all over the world, even though a few telegraph systems went a little crazy because of power surges. It didn't have much of an effect on everyday life. Don't forget though that this was 20 years before the light bulb was made. That was in the past. Things would be very different right now. Coronal mass injections are common, but they can be different sizes and move in different directions. So the question is, what are the chances that something like what happened in Carrington will happen today? And how would it change things? So, what is going on at the sun, on the surface of the sun? When we talk about the solar wind and space weather, the sun is made of magnetic fluid. And when that magnetic fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions, which are called mass ejections. And these explosions are huge, sending out 1 billion tons of material at 1 million miles per hour. So we want to know where these things are going, because if they move toward Earth, they could affect the technologies we use. There's a very famous event in Quebec in 1989, where some power systems were disrupted for many hours in October. We've heard about the Carrington event, which happened in the 1800s. What would happen if it happened today, and how would it affect us? If we think about what we use satellites for now, we have GPS spacecraft that help us find our way, communication satellites, weather satellites, and even the stock markets are linked in some way. But we also have bigger power grids and a lot of wireless technology, and we don't know how they will react. How likely is it that something like the Carrington event could happen again? We know that the sun can still make these things happen. In 2012, there was an event that luckily didn't come toward Earth, but it did pass over one of the spacecraft we used to watch, the solar wind, and it pushed all the sensors on that spaceship to their limits. From what we've learned, we think that was at least as powerful as the Carrington event, and maybe even more so. It's just a coincidence that a big CME and one that's headed toward Earth both happened at the same time. And that's mostly just a matter of luck. We either get one or we don't. And how do we make predictions? Can we predict what the sun will do in a week, a month, or a year? Once ACME is up and running, we can start making predictions so that we can figure out how big it is, how fast it's moving, and most importantly, where it's going. All of this sounds very scary. Space weather is a problem, and the UK government knows this. The National Risk Register lists it as about as bad as a pandemic of flu, so the people who make spacecraft are trying to find out what the most extreme conditions are in space, so they can make them so that they can handle those conditions to a certain degree. Both NASA and ESA are getting ready to send satellites into space that will get closer to the sun than ever before. The Met Office's Space Weather Operations Center opened in 2014. It is one of only 3 places in the world that can predict the sun's effects on Earth around the clock. So far, the sun has had almost no sunspots, and the site that faces Earth is not expected to have any more sunspots or CMAs that are important. So luckily, there isn't much going on right now, and things don't look too different in the long run, so spacecraft satellite power supplies should be safe for the foreseeable future. Trouble is, the foreseeable future in space weather forecast is at most just a few days, and we still don't know a lot about CMEs, like where they're going, how big they are, or when they might happen in the future. 2 new solar probes will get closer to the sun than any other spacecraft has ever done. The Parker Solar Probe was supposed to be sent into space, and its destination will be close enough to the sun's surface to fly through the source of the most energetic solar particles. The Parker Solar Probe is an exploration mission that will measure the gas and magnetic field near the sun to figure out why this stuff is spreading out into the rest of the solar system. And this is the Solar Orbiter from ESA. The Solar Orbiter might find out how sunspot flares and coronal mass ejections on the sun's surface are related to the solar wind. Solar Orbiter success will be very important for our understanding of how the sun works. We think that the sun's magnetic field is made in a way similar to how the Earth is, but it is much more dynamic and changes all the time. We have an 11-year sunspot cycle, during which the sun's magnetic fields move towards the poles and the polarity changes. On top of that, the magnetic field goes out into the solar system and flows over all of the planets. Solar Orbiter will measure these magnetic fields for the first time, and it will also give us the chance to watch the magnetic fields move to the sun's poles. To do this, Solar Orbiter will take pictures of the sun's atmosphere and measure the number, speed, and temperature of the particles moving across the space between the sun and Earth. But the magnetometer, which is made to measure the tiny magnetic fields in space that are carried by the solar wind, could be one of the most important and sensitive instruments the sun is ever present in our lives. It gives us light, warmth, and even life itself. For Richard Carrington, who was the first person to record ACME, it was just a strange event. But now we know that these things can do a lot of damage to the world we live in with new satellites. And more observations, we might be able to learn more about these events and predict when the next corona mass ejection will happen